The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and welcome to Advanced SQL Programming for SQL Servers Indexing for Performance webinar. My name is Jeff Garbus, and you're going to be hearing my voice for about the next hour. The material in this section is material that I've been presenting at SQL Saturdays for a while. It's been pretty well regarded. I've gotten some great feedback on it. This is also a small portion of a full week class that we do, which is Advanced SQL Programming for developers. It's basically a performance and tuning class for developers. That's also been a very popular class. That said, the sales portion of the show is over, and I'm going to skip right past the who we are and what we do, because at this point, I think you all know we're a consulting company, and move right into topics. Before I get into topics, I want to talk about two giveaways that are going to happen at the very end. We're giving away one Yeti cooler for those of you who are into camping or boating or just being outside. The Yeti coolers are really exceptional ways of keeping food cold for days, weeks, or years. And no, I'm not a Yeti salesman. And for the rest of you who stick around for the duration, we are giving away digital copies of our latest book, which is Mining the New Gold. Data is the New Gold. So that said, let's get right on to indexing. So the topics for today, what we're really going to do is talk about A, how the server uses indexes, B, how you need to use the server to use indexes, and C, how those things intersect. The way we're going to do that is to talk about how the indexes are set up internally, because once you understand that, it'll be very obvious to you how the servers can and can't use the indexes. So that said, the basic topics are search arguments, which is to say column operator constant. A search argument is something in a where clause that allows the optimizer to say, okay, you are limiting the scope of the query. You don't want the entire table. Let's bring just some of the information back. We'll spend a great deal of time talking about clustered versus non-clustered indexes. The big difference there is that we're physically sorted in clustered index order, which means if we're bringing lots of data back, they tend to be on the same page. We'll spend a lot of time on that. We'll talk about the differences between or and how that affects indexing. We'll talk about index covering, which is a way of treating the leaf level of a non-clustered index as if it is the data page of a clustered index. And if that was too much terminology too fast, let me assure you that in about 20 minutes, that will be really obvious. We'll talk about forcing indexes, because everybody wants to be able to do it, even though it's not always a great idea, as well as filtered indexes and a few other assorted topics along the lines of how to ask the SQL Server what indexes it thinks are missing or which ones are not being used. So I'd like to start this lecture off with giving away all the punchlines. So if all you do is pay attention here, you'll get the idea of what the indexes can and can't do. So if I'm doing this live, I always ask the question, who in the room is old enough to remember a telephone book? And the reason I do that is I taught a database class at a local college, Florida Polytechnic, and I found that only 3 people in the room actually had seen a telephone book and held a telephone book in their hands, which just made me feel very old. So I'm going to assume you know what a telephone book is. A telephone book is what we use to look up telephone numbers. It is an index on last name, first name, middle name, and it brings you back an address and the telephone number. So if we have a telephone book in our hand, we're going to use our thumb. The thumb is going to flip through pages very rapidly, and if I'm looking for myself, Jeffrey Garbus, I'm going to look for Garbus. I'm going to flip through until I get to the G's. I'll slow down at GA. I'll slow down a little bit more at GAR. Because I only have 3 characters on top of the page, I'm going to plop the book open, plop being one of my technical words. I'm going to take my pointing device, which is my finger. I'm going to run it down the left side of the page, scanning the page for Garbus. Once I find Garbus, I'm going to move to the next column, which is first name, and I'm going to scan until I look for Jeffrey. At that point, I have the row that I'm looking for. I care about it. I move to the right. I pick up the address and the telephone number. Now, that means that the telephone book is a very good lookup for finding Jeffrey Garbus. So let's take another look at this and ask the question, what if I'm not looking for Jeffrey Garbus, but I'm just looking for all the Garbuses? Well, I'm still going to use my thumb. I'm still going to use my pointing device. But since I'm only looking for Garbus, I'm not going to bother looking over at the next column. The takeaway from that is that an index is good even if you're not using all the columns, because I can use that index to get to that first item, bring the information back without either looking at the second column, and the SQL Server is smart enough to do that. Now, let's ask a different question. Let's ask the question, what if we want to bring back all the Jeffreys? At this point, the telephone book kind of flops as an index because in order to find all the Jeffreys, I have to turn every single page in the telephone book and look at the Jeffreys. Well, that is slightly faster than dialing every phone number in the book and asking, are you a Jeffrey? It's an inefficient use of the index. Now, if you're used to looking at query plans and you see in that query plan the phrase index scan, that index scan means you're looking for all the Jeffreys in the telephone book by scanning every page in the index. What you want to see is index seek or index lookup, depending on the version of SQL Server you're running. Now, what would we do if we wanted to have an index on Jeffrey? Well, we'd create another index, right? So in this case, it would be a separate telephone book. Now, let's stay with that analogy because the telephone book itself is a clustered index. Why is it clustered? Because the data is sorted in the order of the index. And if I want all the Garbuses, they're all going to be on the same page on a good day. But what about all the Jeffreys? Well, this is what we're going to do for the Jeffreys. We're going to have a separate telephone book, which is going to be sorted by first name. Since we sort that telephone book by first name, what we're really going to have there, we're not going to have the address and the phone number. Relational theory says stored in one place, not in two. So in that second telephone book, we're going to have a pointer to the original phone book with the page number and the row ID that corresponds with the Jeffrey. What this does for us is give us a very fast way of getting to the actual data and the ability to store the actual data only one time, which is critical to us. So, clustered index on Garbus, non-clustered index on Jeffrey, and we've got a win. I'll be asking a lot of thought-provoking questions or things that I think are thought-provoking over the course of the next hour or so. And the first one is, why do we index on last name, first name, and not on first name, last name? Well, this is not a Bond, James Bond type of thing, and it is not because telephone books have been around forever, and they have been around for over 100 years. The reason is granularity. So, as we ask the question, how many Garbuses are in the phone book, the answer is not very many. If we ask the question, how many Jeffreys are in the phone book? Well, I've got about 100 people on this webinar right now, and there are 5 Jeffreys, but there aren't any other Garbuses other than me. This is kind of typical. In fact, I find the smaller group I'm in, the more likely I am to have multiple Jeffreys. And being in a room of 6 people with 4 Jeffreys is something that not everybody gets to experience. So, what we try to do is take the more granular column and put the more granular column first. And the reason for that is simply so that we are looking at fewer operations or fewer rows to find the data that we care about. So, what does a SQL Server actually do in order to pick this up? Well, we've got 3 options. We have a table scan, an index search, and a covered index search. The idea behind a table scan is we pick the first row, the first page that is pointed to by the system table, read it, check the header points to the next page, bring that page in, check the header of that page, and we repeat that until we're basically through the entire table. That is, the header is now pointing to something null, means we're at the end of the scan. A table scan is what makes the relational myth true, which is you tell the server what you want, not how to get it. Next, we have an index search. The index searches that we're going to be talking about are B-tree type searches. And this is 99.9% of all the searches that you're going to do in a SQL Server. And that is the main focus of the next hour. Finally, we have a covered index search. A covered index search is a special case of search, which we'll talk about shortly. It basically means that the data that you want is already in the index, and we don't have to separately go out for it. So starting with the table scan. We talked about what a table scan is. Table scans are expensive because we have to make a lot of page requests. And I talk about performance in terms of the number of page requests that we have to make. The table scan may be the best way to resolve a query. If I do want all of the rows in a table scan is the best way to get them out. There's no reason to pop in and out of an index structure. We will occasionally try to do a partial table scan. If, for example, I want everybody whose last name starts with an S through people with the last name starting with a W, I may want to come in at the S's, scan the table, and then start when I get to the X's. Here's a sample table search. I'm selecting from a table where an ID is equal to 1. I do happen to know that there is no index on that table. So the query plan is going to look like this. It's going to tell me I have a table scan, and that table scan is taking up the lion's share of the cost of the query. We verify, or at least I verify, table scans with set statistics IO on. This is very old school. There are newer ways of doing this, but I don't think they're as effective because they don't count the things that I care about. When I set statistics IO on, what I get is the number of passes I'm making through the table, the number of pages I'm requesting, the number of pages that I had to go out and perform a physical read for, and the number of read-ahead reads. Now, there's a lot of documentation out on the web which is incorrect, which describes read-ahead reads as a performance degradation. In fact, they're a benefit so that you're not swapping your process out as often while you're performing your queries. So, statistics IO1. This is also a great way. Every once in a while, I'll get asked the question, hey, Jeff, what's faster, approach A or approach B? Well, my approach is to code them both and find out which one has the fewest total logical reads, because that way, rather than timing it and wondering how much was in cache, how much was on disk, was something else going on at the OS level, did the network get busy during one of the scans, this actually tells me how much work is being performed. Purpose of this slide is to mention that you can perform a table scan even if you're not performing a select. Here I've got an update and I'm incrementing the IDs. Note there is no where clause. If I have no where clause, I am going to update all the rows in the table, obviously, but there's another gotcha there. If you do not have a matching index to correspond with your update, you will put a table lock on the table for the duration of the update. So let's restate that. Even if you have a where clause, if the where clause does not have a matching index, you get a table scan. I've walked into situations where everything went really well during the user acceptance testing because they had 30,000 rows of data in there. And then they moved from user acceptance testing into production where they had 30 million rows of data in there, and suddenly things were slow and there was a lot of blocking. And the reason for that was that, well, SQL Server will mask the time that it takes to scan 30,000 rows of data because, after all, you're going to do that in under a second. When you're scanning 30 million rows of data and everybody else is trying to perform updates and data modifications, that's a problem as well. Note in this case, the cost of updating the entire table was less than the cost of scanning the entire table. Why is that? Well, when we're updating, we're only recording changes. We're not pushing those changes off to disk except out to the log, which is generally faster I/O and less information because we're only logging the changes. We're not logging necessarily everything that corresponds with the change. So, next question is, how do we know which indexes we're going to use? Well, if you go back to the talk we did on telephone books, that can actually be pretty obvious. But let's talk about the less obvious ones, what the index structures look like, and how we're going to pick something. Topics for this section include optimizer selection criteria, when the indexes are going to slow the access down, and index statistics. So I mentioned earlier that this class is part of a larger class, which is a one-week performance and tuning for developers, and in that class, we do talk a good bit about the different phases of optimization, but for our purposes, we're really talking about just as the index selection phase. So during this index selection phase, we're going to identify which indexes match the where clause and the join clauses. So let's think about that one for a second. What this bullet is implying is that we're only going to use an index if there is a corresponding search argument in the where clause or a corresponding join clause. This is true pretty much 99.9% of the time. There are some exceptions where you might perform index scans instead, but those are extremely unusual and very specific. The optimizer will do two other things. It will estimate the rows to be returned and the number of page reads. It does this for two reasons. The way it does this is it looks out at the histogram that it's built at index creation time, which may or may not be kept up to date automatically and may or may not be kept up to date by your DBA. The reason it does this is that if the number of page reads exceeds the number of rows, which it might, then it's going to be faster to table scan. So you want to make sure you're not table scanning more than the number of pages, you're not reading more than the number of pages in the table. You don't want to read them all twice. And we'll talk about how that might happen. The other reason is that this row to page ratio very heavily drives what's going to happen during your joins. In fact, the join order matters a lot, and you want to make sure that the inner join is performed as few times as is possible. So, as we start looking at the where clauses and the join clauses, what we want to do is match the search arguments or the join clauses up to existing indexes. Now, the index is generally going to correspond with the search argument of the type column operator constant. ID equals 1. Date equals today, 8/29/2018. A useful index, note that not all indexes are going to be useful, will specify some sort of boundary for the result set, because once again, we're trying to restrict the number of rows coming back. In this example, it says where date of birth is between 3/3/1941 and 4/4/65. A couple of interesting questions pop out of that query. I'm going to start with the direct one, which is, hey, you said this has got to be column operator constant, and here I have column operator date and date. Well, what we find is that because we can take date, the between, and say between is greater than or equal to, and that is an operator, 3/3/1941, and date is less than or equal to 4/4/65, the optimizer will treat this as a search argument because it can syntactically break this down. I will make that differentiation a little bit about the syntactic breakdown versus performing a function. So this actually is a search argument, date of birth between those dates. Now let's talk about two other things while I've got that. I specify 1941, but I don't specify 65. I find about 60% of people are aware that if the date is less than 50, we assume it's 2000 and something. If it's greater than 50, we assume it's 1900 and something. So 3/3/41 would be assumed to be 2041, whereas 4/4/65 is assumed to be 1965. The other one that I bring up, which shocks some people and other people just sort of shake their heads and go, yep, I fell for that one once, is what the between really means. So let's say, just for the sake of argument, that I've got 1,000 rows between 3/3/1941 and 4/4/65. What happens if I reverse those and say between 4/4/65 and 3/3/1941? How many rows do I get back? Well, I'll generally get a few people quickly saying the same 1,000 rows and a few people quickly saying 0, and a bunch of people going, I wish I'd thought of that one before, I'm not sure, or why are you asking me this early in the morning? The correct answer is it depends what version of SQL Server you're running. If you're running a recent version of SQL Server, the ANSI Standards Board, now the ISO Standards Board, has defined a between as greater than or equal to the first value and less than or equal to the second value. But that was not always true. That happened with the ANSI 89 SQL Standard. So, summary, column operator constant, this can be syntactically changed. Now, an index may be used if any column of the index matches the SARG. So, here I have that telephone book lookup that we discussed, an index on last name, comma, first name. As I look at that index, I ask the question which queries are going to use it. So, the first query, first name equals Jim and last name equals Smith. Now, the columns that are listed in the where clause are not in the same sequence as the columns listed in the index. This does not matter at all. What matters is the order in the index and the fact that, honestly, this lookup is kind of built for that index. Let's look at the next one. Select from authors where the first name is equal to Jim. Is that index a good index? Well, I have people coming up to me and saying, Jeff, I have an index on A, B, and C, and I'm doing a lookup on B. It's not using the index. Why not? And all of you can now turn to that person and in a non-condescending tone, talk to them about telephone books and why it won't use that index. Because what it's going to have to do is an index scan versus an index seek, and the table scan may be faster than the index scan. Finally, and this is a trick question, where last name is Smith or first name equals Jim. Well, here's the thing. For an or, I actually need to do two lookups. I need to do the lookup and bring back all the Smiths. I need to do a lookup and bring back all the Jims. Then I need to eliminate the duplicates because Jim Smith would come back twice and then return the result. So because I need two lookups, I will consider using two indexes. I do have a matching index to bring back all the Smiths. That index on last name, first name is great for bringing back the Smiths. The index on Jim, well, gee, I don't really have an index on first name. I have to do an index scan to get that. So what you may see is instead of two steps, you may see an index scan, you may see a table scan. If you see an index scan or a table scan in your query plan, this almost always means you're missing an index. So don't assume you're using the index well just because the word index appears in the scan. So let's talk about types of indexes, how the optimizer is going to choose between them. This says when indexes slow access down. I'm going to cover that right now. I get these calls on Friday afternoons, and these calls go along these lines. Hey, Jeff, we have a performance issue. We've been working on it all week. Haven't been able to figure it out. I talked to somebody that I met at a conference last week. He said, you fixed this problem. Can you come fix mine? I always ask, well, who recommended me? Because I like to send a bottle of wine to say thanks. And I only find out about a third of the time. On this occasion, I did not know who it was. They did not know who it was. I suspected who it was, and I called them and I said, thank you. But the short version is they said our inserts are taking 3 to 5 seconds. And my first question was, well, what else is going on in the system at the time? And they said, nothing. We're doing this in isolation. So my next question was, what's the trigger doing that's on the table? Notice I did not ask if they had a trigger. And the reason I did not ask if they had a trigger was it was late on a Friday afternoon and I was tired. And I'm sure everybody gets that way on a Friday afternoon sometimes. They said, well, how do I find out? And I said, there's your first problem. They went and they took a look, and there was, in fact, no trigger on the table. My second question was, how many indexes do you have on the table? And they asked, how do I tell? And I said to myself and to them, there's your second problem. We went and checked, and it turned out they had 120 indexes on the table. Now, 120 indexes is a lot of indexes, but they only had 30 columns on the table, which means they probably had at least 70 too many indexes. This is something that you see more often than you might think, because the SQL Server currently includes a database engine tuning advisor, which when it sees a bad query will recommend an index. And if you arbitrarily create the index every single time it makes a recommendation, you're going to have a lot of indexes out there, and many of them are going to be redundant or be easily combined. We'll talk about that in a little bit. So too many indexes slow access down. Index stats and usage we will cover separately. So the server has three basic types of indexes. The first is a clustered index. A clustered index causes the data to be sorted in the order of the index. The second type is a non-clustered index. A non-clustered index is a way of pointing back to the clustered index to get the data. That is that telephone book and additional telephone book that we talked about. Finally, we have a full text index. The idea behind the full text index is that when you have a varchar max column and you're storing emails in there, you want to be able to search that in an efficient manner, and the full text allows you to do that efficiently. The full week class that we do has that chapter in it. Not everybody uses it. It's out of scope for this particular session. But we are going to spend the next 10 minutes or so on the next two slides. I'm going to be going back and forth, talking about the differences between clustered and non-clustered. And I warn you in advance, I'm going to be contradicting a lot of what many of the white papers on the web say, because they're wrong. And you'll be able to demonstrate this for yourself experimentally when we're done here, and it will be absolutely crystal clear to you, and you'll scratch your head and wonder why they do it the other way, but I'll answer that question as well. So, a clustered index physically sorts the data in the clustered index order. Here I have a clustered index on last name. How do I construct this? I take the table and I sort it by last name. I put those on data pages which are linked together. So on the first data page, I have Albert, Alexis, Amundsen, Baker, and Best. The next page is going to start with Best and move forward from there, and it's going to keep going all the way down. The data page in a clustered index is actually the leaf page of that index. So once I have the leaf page, I start building out the intermediate pages. The way I do that is I take the first entry from the first page, which is Albert, and I put it in that intermediate page. Then I go to the next page and grab the first entry, which is Brown, and I put it in the next page. And I repeat that until I have an entry for every page in the data pages. So let me say that one again, it's important. The size of the intermediate data page level, the first data page level, is directly proportional to the number of data pages that I've got. If I have 1 million data pages, I have 1 million entries in that leaf level. Now, I continue building the levels out. I go out to that next level, and I build it exactly the same way as I built the first level. Take the first entry, which is Albert, bring it in. Take the first entry, which is Jones, bring it in. Take the first entry, which is Mason, bring it in. And I do that until I've hit the end, and then I have my next level. Now, when I get to a level that has one page in it, I've got the root page, and that root page is my basic entry point for that index and for that data. Let's follow it down. I want to find Joe Baker. Well, Baker's between Albert and Jones. I follow the Albert pointer down. Baker's between Albert and Brown. I follow the Albert pointer down. I'm now on the data page. Once I'm on the data page, it doesn't matter whether I do a page scan, whether I look at the row offset table at the end of the page, whether I do a binary search on the page, because the cost of acquiring the page is so much higher than the cost of searching it that it simply doesn't matter. My cost of finding Joe Baker with this clustered index is 3 page requests. I requested the root page, the intermediate page, and the data page. Hopefully that was all clear, because I'm about to add several layers of complexity after doing the non-clustered index. The non-clustered index, well, we've already got the data pages sorted by last name. This is pretty obvious. And also what should be obvious is that we can only physically sort the data one way, which is why we can only have one clustered index. So all the rest of the indexes are non-clustered. What we're going to do is take each entry from the data page, because we need to be able to find every entry, and put that into the leaf page. Let's translate that. Again, If I have 1 million rows of data, I have 1 million entries in the leaf page. So the size of the clustered index is proportional to the number of pages of data. The size of the non-clustered index is proportional to the number of rows of data. Once I have that leaf page for the non-clustered laid out, I sort it. Once it's sorted, I build out the intermediate pages of the non-clustered exactly the same way I did with the clustered, which is first entry from the page, move it out, first entry to the page, move it out, etc. And I do that once again until I get to that root page. So let's say, just for the sake of argument, what I want to find here are all the Amy's. Amy is between Amy and George. I follow the Amy pointer down. Amy is between Amy and Bob. I follow the Amy pointer down. Now I'm on the leaf page. I have my list of Amy's. Note that I don't have Amy's address and phone number yet. I still have to go to the data page to get that. So for each Amy, I read the data page that Amy resides on, the row for Amy's data resides on, and I bring it in. So for 2 Amy's, to bring back the telephone numbers, I've got 1, 2, 3 index levels plus 2 data pages to read for 5 total I/O requests. Let's take that the next step. What if I have 50 Amy's? Well, if I have 50 Amy's, I've still got those same 3 leaf pages to read. Then I have to make 50 data page requests to bring the Amy data in. So 53 I/Os to bring back all the Amy's. Hopefully everybody's still with me. I'm going to go back to the clustered index now. What if I have 50 bakers to bring back? Well, I've got 1, 2, 3 page requests. Where are all the other bakers? Well, I'm physically sorted by baker. On a good day, I've still got all the bakers. I've got all those bakers on one page. I only have 3 page requests. On a bad day, I read the next page in the page chain. I pick up the next set of bakers. So, bring back 50 Amy's, 53 page requests. 50 bakers, 3 page requests. So, the question I need to ask is, what's more efficient for bringing back 50 bakers? Well, clearly, the clustered index. If I'm always bringing things back on first name, well, I would want a cluster there. Now, if you are like anybody else in the world, you have, do I have this thing built out? Thought I added the slide. I guess I didn't. I'll have to add that soon. You have a slide or a situation that goes something like this. Let's say you have an invoice header, invoice detail relationship. Your invoice header has an invoice header ID, which is usually an identity column and usually has a primary key, which is usually a unique clustered index. You have an invoice detail table. The invoice detail table has an invoice detail ID, which is generally a unique primary key, which is on an identity column. Inside that table, you have a foreign key, which is the invoice header key. And that invoice header key is used to bring back all of the invoice detail IDs for the invoice header. Now, whether or not you process invoices at your shop, you have something that looks like that, I guarantee it. Now, let's go back to our knowledge of indexes. At almost every single shop, you have a clustered index on both primary keys, and you have a non-clustered index on your foreign key. So what happens when you bring in, give me all of the details for the header? Well, you're going to go through your index levels. You're going to find out you have 50 entries for your invoice detail and make 50 page requests. For some of you, the light bulb is already going off. What if we switch and make that foreign key the clustered index and make the primary key a non-clustered index? I assure you can do this with a click. At that point, when I'm joining from the header to the detail, now I have 3 IOs instead of 53 IOs to bring back the 50 detail rows. I just made your invoicing report 50 times faster. We don't really just go from header to detail, do we? We go from detail to description. We go from detail to quantity. We go from detail to pricing. We go from detail to addressing. We go to the customer address. By changing some of your non-clustered indexes to clustered indexes, you can make your reports 50 times 50 times 50 times 50 times faster. I have literally made multi-hour reports come back in seconds simply by changing the index types. I've done this more times than I can count. My personal record is a 48-hour job that I took down to 23 seconds. There's a fun story behind that one, which I'll share at the end if anybody is interested. I'm going to save it for time constraints. But it involved making a New York middle manager giggle, even though his CEO was pulled out of his play on a Friday night. Anyway, let's go back to indexes. Non-clustered indexes. We've talked about the fact that the clustered index is going to be much faster for a range of data when you're bringing back lots of data, multiple rows. How about when you're bringing back just one row? Give me all the rows for this one ID. Well, what we find is that the clustered index tends to be one level less, and the non-clustered index tends to be one level more. Why? Because of this leaf page. An entry per row versus an entry per page just tends to make the index levels one more deep. You don't have to worry about this, but do be aware of it. Measuring this, well, you can always look at the physical data pages, but measuring this, it's very difficult to measure the difference between 3-page requests and 4, unless you're doing it a million times, in which case it really does add up. So we tend not to worry about adding an additional non-clustered index. From an overhead standpoint, we tend not to worry about adding one more non-clustered index. Let's talk about using the non-clustered index just a little bit more. Now, I would like to draw your attention to these leaf pages. These leaf pages right now have first names in them, and they're physically sorted, and the pages are chained together. This is kind of interesting. Let's pose a question. How many Amy's do I have? If I say select count star from the table where first name is equal to Amy, I can use this index, come in down to the leaf page, but interestingly, once I get to the leaf page, I don't have to move to the data page. There's nothing there that I care about. As a result, I can treat the leaf level of the non-clustered index as if it is the data page of the clustered index. What this does for me is give me the one time that a non-clustered index will be faster than a clustered index. Why? Because I may have 100 rows of data on a data page and 1,000 rows of data on an index page. The data is more compact, fewer rows to scan, fewer pages to scan. This is called index covering. This has been a trick forever. Back in the days before we could simply add columns as an include to our index, we would add columns in sequence and say, okay, I'm currently indexed on A, B, and C. Now I'll index on A, B, C, and D. Well, D is not in your query. No, it's not, but it's in the select list, and this saves me from having to go off to the data page. The optimizer is aware of this trick. The optimizer will take advantage of this trick, and this works out really well. What's left? I think those are the biggies. I did 15 minutes instead of 10 on clustered versus non-clustered, but I'll get through the rest of this stuff very quickly. I know it says page 18 out of 60, but we've covered the really important stuff, and I'm going to fly through a lot of the rest of this in case people have questions at the end. So, clustered index tends to be 1 IO faster. We talked about ranges of data. We can use the index to avoid order by. The clustered indexes are a bit slower. Index covering is very fast. You do always want to have an clustered index on your table. Here's why. Let's take a look at this data page again and ask the question, what if I didn't have a clustered index on here? And I insert John Smith. Where does he go? Well, if you don't have a clustered index, the data is stored as a heap and it gets stuck at the tail end of the table. Well, that's not necessarily bad, but what if 1,000 people are trying to insert all at the same time? Well, you get a hotspot at the tail end of the table. And that, by the way, is another reason I don't like to cluster on those identity columns. Next question, what if I delete Joe Baker, and then Fred Amundsen, and then Amy Alexis? As these pages start to get empty, they do not get reused if you're storing the table in a heap. Because when I insert the next Joe Baker, it doesn't go on the right data page. It goes once again at the tail end of the heap. So in order to keep our pages, our data pages balanced, always want to have a clustered index. So using the indexes, clustered, great for ranges, sorts, sequentially accessed columns, join columns as we discussed with our primary foreign key example with the invoice header and detail, static columns. There's another good one. What happens when Elizabeth Best marries Irving Masonelli? Well, in the US, Elizabeth will frequently change her last name to Masonelli, at which point her row will move down here. What happens then to every single non-clustered entry that's pointing to Elizabeth? It's got to change. So when we talk about picking a static column for the clustered index, it's to avoid row movement causing excessive updates to the non-clustered index structures. Other index limitations, 16 columns, 900 bytes of width. Note that the 900 bytes of width is enforced at runtime and not at creation time. So if you take a varchar 1000 column and create an index on it, the server will say, okay, but it's not a good idea. And it won't be until runtime when you exceed the 900 bytes that you get burnt. This box is my soapbox slide. So most of the white papers out on the web say you should always create an identity column and it should always be your primary key and you should always have a unique clustered index on it. And if you're building an application in your garage and you don't know a thing about performance and tuning, it's not a bad recommendation because the server does a lot of very smart things. But be aware that a primary key is a logical concept. An index is a physical concept, whereas there's a strong correlation between the concepts of key, logical, and index, physical. You can intelligently choose which ones are clustered and which ones are non-clustered. Very important, and this is going to directly key to performance. Now, let's talk about what the optimizer will do. In these simple single table lookups, which is all we've done so far, let's choose indexes to optimize the query. So in the first one, select title from titles, where title is equal to stranger in a strange land. If I were picking an index, I would choose an index on title. That's where I've got the where clause. I would consider an index, a clustered index on title, because, well, I'm frequently doing lookups by title. I would also consider a non-clustered index because I've got index covering working for me, and that might be the fastest way to get the data back. Select title from titles where prices between $5 and $15. Now, this becomes interesting. If I create an index on price, and I'm at, say, a Barnes & Noble, I can have a very large number of books between $5 and $15. This may exceed a big percentage of the table. As I start to exceed a large percentage of the table, let's think about this one for a minute. Let's say that I've got, let's go back to the Amy list, okay? So going back to the index, let's say that rather than having, a normal distribution of names, we're at an Amy convention. We've got 1 million Amy's and 1 million non-Amy's. What is faster, to table scan or to use an index, a non-clustered index? Well, if I'm going to use a non-clustered index, I've got 1 million page lookups to bring back to Amy's. So unless I only have 2 rows per page, guess what? The number of lookups I need to perform is going to exceed the number of pages of data. So it's actually faster to table scan. And what you find is that ratio gets very close to about 50 to 1 in terms of where your break even lies. From a practical standpoint, if we're going after, half or a third of the data, it might be 10 times slower to use an index than to do the table scan. So simply creating an index on price is probably not going to be efficient for us or not useful. Now, an index on price, title, which gives us index covering, could be a very good solution if you're going for a non-clustered index. The third query really is a way of driving home the data distribution point, which is between $5 and $15. I may have tens of thousands of books at a Barnes & Noble in my price range. It's relatively narrow. That's a $10 price range. But if I come up to a much larger price range, a $100 price range, I may not have any books in there. So this might be an interesting solution if I have a non-clustered index. I need to put a non-clustered index just on price. Here I'm quantifying a little bit. If I have 2 million titles, I'm fitting that on about 14,000 pages. 138 rows per page, a million rows in the range. If I use a clustered index, that's pretty efficient because then I've got, 7,000 pages to read, about half the pages. Non-clustered index, I've got 1 million page reads. That is one for each of the titles I'm trying to pick up, which obviously is slower than 7,000. If I just do a table scan, that's 14,000 reads, which again is, 50, 60 times faster than using the non-clustered index. And I'll see this with some amount of frequency. I'll get to the point where folks say, Jeff, I've got an index on A. I'm doing a search on A. You told me this is the way to create the index. And I'll take a look at the granularity of data, and they'll index on something like gender. Well, 50% of the data is male, 50% of the data is female, roughly. You're going after 50% of the data. It's going to table scan anyway. That gender column is not likely to help because of the way indexes do work. So it is feasible, even likely, that a table scan may be faster than the non-clustered index. The server is going to perform the math on that at optimization time. So I've got about 7 minutes left and 33 slides to go through. I'm going to be talking a lot faster, effective immediately. As we are performing an OR, the idea behind an OR is that with an AND, we will always pick a single index. With an OR, we'll pick up multiple indexes, one for each pass of the data. So the moral of this particular query is that I'll pick an index on price, title, and another one on type, title, and then I will combine the data. The AND, I will pick price, type, include title, or type, price, include title, depending on the granularity of type and price. If I have first name in, the useful thing to know is that I will make multiple passes of a single index, one's for the Freds and one's for the Sallys. We've talked about the ORs, we've talked about the INs. Take a brief talk about the OR strategy. The idea behind the OR strategy is when we have an OR, we can do a table scan, which goes through everything and performs a filter. We can use a multiple match index. Here's a situation where the key is going to be 1, 2, or 3. Because I know that there is no overlap there, the key is going to be 1 or 2 or 3. It can't be all of them or any combination of them. I can just stream those back and pass them into whatever processing I'm doing. This, by the way, is a great use of parallelism. Or I can perform the OR strategy, which is perform each of the queries separately, merge the result sets, and bring it back. Note that the cost of merging the result set here is about the same as the cost of retrieving the data. This merge is very expensive. So people don't tend to think of ORs as something that is increasing the cost of the query, but be aware that it is. This next set of slides is for the classes that I'm doing, and I talk a lot more about index covering and how that works. We've already discussed the topic. We've talked about composite indexes, which are, do we use last name, first name, or some subset thereof? The rule here is that we will tend to use an index if the first column of the index is being used. If not, we may do an index scan, which is not efficient, but may still use the index. So make sure you take a quick look at those. As far as index statistics go, at index creation time, the optimizer creates a histogram of the way the data tends to get laid out. What that means to you is that we know if we've got 5 books between $5 and $15 or 50,000 books between $5 and $15 because that information is stored in a histogram, roughly. The catch is those histograms get out of date. So what you need to do is make sure that your DBAs are aware of the fact that you need to update your statistics. So I'm going to skip the math part of the data distribution and just simply say the data distribution for the statistics is very critical to the order you place them in the index, as well as whether the optimizer is going to use them at all. We can take a look at this with the dbcc show statistics command. This is not well documented. In fact, I almost never find this when I do Bing searches. And by the way, you should do a Bing search instead of a Google search. What this does is allows me to take a look at the size of the table, the sampling, the density. The density is the number of unique values, or 1 over the number of unique values, what keys are in the index, what the ranges are, how many rows are in the range. Very useful way of finding out what is actually going on with the stats. Also will tell you when the stats were last updated, which can be very critical. Logical page requests are for the purpose of figuring out what the cost of a query is going to be, and the optimizer will cost this for each matching index and for a table scan and tell you which one is best. Now, we can force an index selection. In general, if you're forcing an index selection, it means there's a problem. The optimizer can't figure out the fastest approach. Most of the time, it's one of 2 things. A, your statistics are out of date. B, the query is written horribly. It needs to be rewritten. If the query looks good and the optimizers are up to date, go ahead and try forcing it. Very unusual to identify situations where you've proven the optimizer wrong. Do make sure that you document this. If you want to force the index selection, the way you do it is with this. In the select list, in the from clause, after the table, open paren, keyword index, open paren, name of the index, close paren, close paren. I don't even put it on a slide anymore. In the olden days, it was open paren, index ID, which might be a number 0 for the table, 1 for the clustered index, 2 through 248 for the non-clustereds, close paren. The catch is if you drop and recreate an index, you're using the wrong index. You're forcing the wrong index. So if you're going to force it, do force it by name. Filtered indexes are brilliant. Filtered indexes were introduced around SQL Server 2008 and started working in 2008 R2. What they allow you to do is index on a smaller subset of data. So my favorite example is you've got a process table, somebody puts an order in it, and you want to know if it's processed or not. So you want to bring back the most recent one that hasn't been processed yet. Well, if you have a processed flag, which is 0 if it hasn't been processed and 1 if it has, you can create an index on date where processed flag equals 0. And therefore, you can quickly identify in this tiny index, rather than the big index, the most recent non-processed index. I do use these with some degree of frequency. So, Identifying missing indexes. There are two things that I do if I go into a shop to do a health check. One is I look for missing indexes, and another is I look for unused indexes. I have code on my blog to do both. There are data management views which allow you to go take a look, find out what's in there, how often these are used, what the parameters are, what the queries should look like, what the indexes should look like. Do not simply apply all these indexes. It's highlighted in red. Don't just apply them all. Take a look, because you have an index on A, B include C, A, B include D, A, B include E. It should really be one index on A, B includes C, D, and E, rather than 3 separate indexes. Trust me, this is how you get a 4 terabyte database instead of a 300 gigabyte database, and I am not making those numbers up. I had a gig where all I did was get rid of indexes for a shop, and I brought 4 terabytes down to 300 gigabytes, getting rid of indexes that were redundant or not being used. Summary. We've talked about a lot of topics. We're not going to do a lab because we're not taking a class. But at this point, I'd like to point you to my blog. The blog does not contain, hey, I took my dog to the dog park this weekend. It contains the code that I use and reuse. You're welcome to go there, take it, borrow the code, reuse the code, whatever makes you happy. Contacting me is right up here. For those of you who want to download a book, send me an email that says, I would like a copy of the new book, and I will send you instructions. For those of you who would like to be entered into the drawing for the cooler, send me an email that says, I would like to be entered into the drawing for the cooler. That's all it takes, and if you want to do both at the same time, that is fine as well. There will be a cooler awarded, and everybody who asks will get a download code for the book. At this point, I think I'm pretty much done. If you want a copy of my latest Transact SQL book, 35% off using the code GARBUS. If you go to jdlearning.com, if you go to Amazon instead, you can pick it up there. The material that we covered in this class is available in that book. It's also available on our YouTube channel, youtube.com/user/SoaringEagleDBA. We have a lot of these webinars up there. You're welcome to use them. Tell your friends. If you want a copy of this webinar, a copy of the slides, send me an email and say, Jeff, I'd like a copy of the slides, please. Or again, you can go up to the YouTube channel and take a look. At this point, I'm going to go and take a look and see if there's any questions and answer them. Number of pages. I'm not sure what that's asking about the number of pages of what. There's clearly 61 out of 60 pages in this presentation. Number of pages in the new book. I think it's about 120. Number of pages in the Transact SQL book, I think it's in the neighborhood of 400 or 500. Do I have any other questions? Oh, here we go. I do have questions. Highlight the differences between Microsoft SQL Server and Sybase ASE. Wow, I could spend hours doing that one. That is, for the purposes we discussed today, the only real differences are that Sybase does not have include syntax, and it does have a feature called function-based indexes, which is very cool. I have one keyword that says remember. Oh, I'm old enough to not only remember telephone books, but I also remember when they were thin. That's funny. Please comment on these items, but it doesn't say what items to comment on. Indexes having low cardinality, like yes or no. Oh, I see. Comment on these. Yes, low cardinality, yes and no, rarely get used, but they're great for filtered indexes. Determining unused indexes and dropping them. I have code for that on my blog. Go look at the code. Last is sometimes used with vendor packages. Yeah, vendor packages are horrible. I spent a lot of my career taking a look at third-party software and interacting with the vendors and saying, add these indexes and get rid of those. Fortunately, after having written 20 books, they sometimes listen to me. Will this recording be made available for download? Yes. Go to the YouTube channel for that. Vendor packages we've discussed. Download, yes. Something on the execution plan that identifies the estimated number of pages. Yeah, if you hover over the icon, you can get a lot of that information. Resources to get started. Yeah, pick up my book. It's got a lot of information on it. With the index, can it be a variable? Here's the problem with variables. Variables are resolved at runtime, not at optimization time. So if it's going to use the index properly, it will frequently have to recompile. Much longer topic. Can you repeat that? Put the non-clustered on the foreign key. I'm recommending that you cluster on the foreign key and non-cluster on the primary key. Estimated number of pages, not usually. Dropping and recreating indexes in the ETL process. That's something you have to measure. Is it faster to import lots of data with the indexes on, or is it faster to recreate them afterwards? I have a number of compliments here. Thank you. Does the between clause assume the percent of the rows in the table are returned? It does it based on the columns that are passed in. Today's session is SQL Server. I do not have a matching session on Oracle. Do I always use foreign keys? I don't always define foreign keys. I always have indexes on them, one way or the other. Are clustered indexes actual on SSD drives? They're on whatever drives the base table is on. So when you place your table on a drive, that's where the clustered index goes. I do like solid state and flash storage. Can we create column store index on existing fact tables? In general, you can now, if you're running enterprise, you can create the index with online equals on, which generally doesn't hurt the data. Which is more important, a clustered or non-clustered index? I need a context for that one. Opt-diag, that sounds like a Sybase question. How do we get the presentation in the book copies? Hopefully I've answered that one at this point, which is send me an email and a request. Does Dynamic SQL use an index? Yes, it does. Dynamic SQL does use indexes. Thoughts on indexed views? Index views work much better now than they used to. I like indexing the underlying data, but if, for example, I'm using an index view to create a column which doesn't exist in either table but is rather a combination of the two, I will index that. I got a failure trying to email you. Jeff@soaringeagle.guru is the correct email address and should work. All right, I think I got to all of the questions. I'm going to thank you all very much for joining. I will leave this slide up a little bit longer because there's still quite a few people in the webinar. I'm going to stop recording though. Have a wonderful day. Thank you for your time. Please feel free to reach out to me via email at any time. Have a fantastic day.